So thank you for making it to the session this late in the conference. This session's about memory efficient Java code. And memory efficiency is really two things. It's first of all trying to... More volume? Yep. Can you hear me now? Ooh, less volume, less volume. How about now? Is that better? Everyone? Slightly higher? Yep. How's this? We good? Okay, great. So yes, when we talk about memory efficiency, we're kind of talking about two things. One is using the least amount of memory possible when you're writing your application, so keeping it small, but at the same time trying to minimize the amount of work that garbage collection has to do. So there's a cost when you allocate objects and when garbage collection frees them up. So you want to minimize that as well as minimizing your memory footprint. And the two in some ways compete with each other. The best way to avoid object allocation and freeing is to cache stuff. And sometimes that means having a higher footprint. So it's a trade-off between the two. So it's always a decision you have to make, and hopefully this presentation gives you a lot of information on how to make that decision. So before I carry on, who has been to an IBM presentation so far this conference? Okay, then you guys don't need to read this. For everybody else, if you've got a camera phone, you're going to need to take a photo, sign it, and send it back to IBM to say that you've read this and you understand that everything I've said is probably wrong because I'm not very reliable. So me, I work for IBM. I've been there for 13 years, spending all of that time working in what we call the Java Technology Center. So I've been working on JDK development on IBM's versions of Java. And I've had quite a range of job roles. I started off supporting customers, doing consultancy, doing kind of bug fixing kind of work. Since then, I've moved on to doing what we call serviceability, so how to do monitoring and diagnostics. I do the way that we get deployed into the cloud. I do customer requirements and basically the external interface to the JVM and the JDK from IBM. So a lot of the content that's in here is things that we've gone out to customer sites and we've worked with customers on trying to make their applications more efficient. My contact details are at the bottom, including LinkedIn and my email address. And there's a slide share account at the bottom, and that's where the slides will be, hopefully by the end of today, but probably tomorrow. So the session itself, we're going to start off aiming to explain how memory gets allocated when you write some Java code. So you use the new operator to create an object, how much memory is actually used for that object. Then we're going to talk about garbage collection and allocation and freeing of objects and how to try and minimize that. Minimizing that means caching, so we're then going to talk about the Java collections, so the ways of storing objects. And then finally, we're going to talk about an easy mechanism to try to find areas of your application where you've got inefficiencies in terms of memory usage. So starting off, memory usage of Java itself. So you've got an application, just a main class that doesn't really do anything. All it does is it creates a new integer object in which you put the int value 10. So an int's 32 bits in size. So on a 32-bit platform, how big do you think is the piece of memory that Java puts on the Java heap for that int value of 10 that you've got in your integer? So who thinks it's 32 bits, the same size as the int? Okay, 3 or 4 people. Who thinks it's 48 bits, so 1.5 times the size of the int value? Anyone? A couple? Who thinks it's 64 bits, so twice the size? We've got a few more. And who thinks it's 96 bits, so 3 times the size? That's probably about a third of you. And now there's a whole number of people who didn't put up their hands. Go on, admit it. So you've either seen me say this before, or you're a little bit lazy. But the answer is actually option 5. I'm cheating. It's 4 times the size. So when you create just a simple int value and it goes into an integer, the amount of memory Java uses to store that is 4 times the size of an int. So it's quite a lot of memory just to allocate a little bit of data. So the obvious question is, why is that? So when you put that 10 value into the integer, we created an object. And Java objects have got metadata that describe your data. Right, so first of all, I need to have something in this object that tells me it's an integer because you created an integer. So what I've got is called a class pointer, and that points to the integer class. So the way that I know what type of object I've got is the first bit of data inside it points to the class for that type. So it would point to a Java lang string or an integer object or whatever its type is. So I've then got a second bit of metadata, which is flags. So this stores a number of bits of useful information. It has usually a shape bit, it has a hash code, and so on. So there's another 32 bits worth of data that tells me some other stuff about the object. You typically have a lock word as well. So the fact that you can synchronize on Java objects, we have to have a bit of data that lets you do that. So you've often got 3 words, 96 bits worth of header. That's just to have a Java object before you put your data in it. Now, I will point out for some of the more technical people here who've worked in JVM implementations, I'm saying typical. The amount of data does change from Java versions, and it actually changes on different types of objects. We try and do things to merge locks and flags where we can, but typically it's around 96 bytes worth of data just for the Java object, and then you start putting your information into it. Now, if what you've got is and then you have your value of 10. Now, if what you've got is an array object, so for arrays, you again have a class pointer that says it's an array of Java, an array of integer. You then have flags in the same way, except this one's going to have a shape bit set that tells me it's an array object. I'm going to have a lock word as before, but I have to have an additional field, which is the size of the array. So I know that this is either a 1-element array or a 10-element array or a 1,000-element array. And this actually means the maximum size of an array is the maximum size of that size number. So it's 32 bits worth of data tells me how long my array can be. And then I have an int value on the end. So to store an int in an integer object, so there's a 4-to-1 overhead. To put a single int into an integer array, it's a 5-to-1 overhead. So arrays are slightly larger. Now, if you move to 64-bit, you have words of data which are 64 bits wide rather than 32-bit. So what we had previously was 96 bits of overhead and then your data. On 64-bit, all of those double in size. So we've got one small value of 10 again, but all of our overhead is doubled in size. And again, it's the same thing for arrays. So where we previously had 128 bits of overhead, that's now doubled to 256 bits of overhead, which means our overhead to store an int in an integer object becomes 9-to-1. So on 64-bit, everything just uses more memory. So moving from 32 to 64-bit, you need to make your Java heap bigger, and you have to accept that it's going to cost you more memory. Now, there is a mitigation for this. Has anybody in the room heard of compressed OOPS or compressed references? Okay, so what this does is it says, where I have a 32-bit value on 32-bit to point to my class, on 64 bits, I can actually use a 32-bit pointer as long as the class is at the bottom end of memory. As long as it's within a small range of memory, I can still use 32 bits to reference it. So for small heaps, and those are heaps under 32 gigabytes, on 64-bit, you can run with compressed OOPS or compressed references, and it stops us using those 64 bits. We use 32 instead. So it looks like this. Whereas on 64-bit without compressed references, we use 192 bits of overhead or 256 bytes of overhead. We shrink back to 32 bits for Java objects and for arrays. So it goes back to what you had on 32-bit. So basically what we're saying is, if you're using 64-bit Java with Java heaps under 32 gigabytes, use compressed references or compressed OOPS. So this is the table of what all of those values inside an object looks like. If you store an int, if you store a boolean, if you store a long, then those are the values. Now, the interesting bit is between 32 and 64-bit, everything's the same apart from objects in the bottom row. So when you move to 64 bits, your object pointers, so if you've got an object with a reference to a string inside it, the amount of memory for that reference to the string doubles as you move to 64-bit. And again, that shrinks back down to 32 bits if you use compressed references. So again, use compressed references. OK, so that was just allocating a simple integer object. Right? We had our single int inside 128 bits worth of memory, and there was a 4-to-1 overhead. Now, what happens if I create a string? So when I create a string, I've got my 3 words of overhead, my 96 bits worth of overhead. Then inside a string object, there's actually a field in there called hash. There's another field called count. There's a field called offset, so that's basically the length of the string and the offset into the string. And then I have a field called value. And value is actually a reference to a character array. And that character array will store your data. So if you create a new string with my string in it, you actually get 2 Java objects created. One that's the string itself, and the other one that's a character array that contains your data, which is my string. So if you total up the overhead again, in this case, we're using 480 bits worth of memory in order to store the 7 or so characters that is my string. So you've got an overhead of 3.75 to 1 for this. If you had a string with a single character in it, your overhead would actually be 24 to 1. So if you have to store just a single character, store it as a char on its own. Don't wrap it in a string object because you'll save a lot of memory. OK, so the summary on Java memory usage is when you create objects, you're creating significantly more data, more memory than the data that you put into it. So if you put an int into an integer, there's a lot more for the integer than for the int. Any object you create is going to be bigger than the data than you'll store inside it. If you move from 32 to 64-bit, turn on compressed references or make your heap size bigger because all of those objects get bigger as you move from 32 to 64-bit. And in more recent VMs, we've tried to optimize this. We try and reduce the 3 words of header down to 2 in some cases. Yes?
Why is compressed references not?
So the question is, why is compressed references not a default option for 64-bit? It is for some vendors, for some releases. So it's best to check that it's enabled for your release. I mean, IBM does for Java 7. We did for our update in one of our updates for Java 6. I know Oracle didn't for Java 6, but it might be there now. In 7, I think they might have. I'm not sure. So check, because it's important. OK, next, object allocation and reclamation. So allocating objects in garbage collection. So when you run your application, you generally end up creating a large number of objects which are temporary. Right? You do a calculation, you add 2 numbers together, and you get a result. Often there's temporary objects created when you do this. Whenever you run a transaction through a JEE system, there's a huge number of objects which are created as you go through that transaction, which are thrown away as garbage. So there's lots and lots of objects being created and destroyed as you go. And that's why there's generational garbage collection. Right? It works on the theory that lots of objects are created and die very young, so there's a nursery collection to clean them out very, very quickly. So the problem with that is that garbage collection is really a tax on your application. The more garbage collection you have to do, the slower your application runs, because your application stops for garbage collection to run. And that time when it stopped running garbage collection, your application's not continuing to execute. Now, GC generally can take up to about 10% of your processing time. In an ideal system, it's more like 1% or less. But in a badly tuned system, it can be 10% or so, and we kind of commonly see that. So you can gain some performance by making sure you create and destroy objects left often. But if the overhead of GC is 10%, the maximum performance boost you can get by minimizing this and reducing the overhead of GC is 10%. And I think Moore's law explains that CPU speeds double every 18 months, so that's going to dwarf what you can do through GC. But we'll cover what you can do and why it's useful. So let's start with string concatenation, something that probably everybody does. So if I've got some code that says I've got string S1 with string 1 in it, I've got string S2 with string 2 in it, and I can say string S3 equals S1 plus S2. So I'm using the plus operator to concatenate string 1 and 2 into a third string. Now, when you run the compiler for this, it takes that plus operator and actually converts it into string S3 equals new string builder, so it creates a string builder, gets the value of the string for S1, appends S2 to that, and then creates a new string with the results. And you can actually see this if you run Java C against it and then run a decompiler or run Java P the probe. It will tell you that this is what's actually happening under the covers. So if we look at what happens in terms of allocating objects, so we start off and we've allocated nothing and we've reclaimed nothing. So we first do string S1 equals string 1. So I create a string object, and that points to a character array containing string 1. So that first line of code creates two objects for me. I then do the second line of code, which is, okay, string S2 equals string 2. So I've got a string object and a character array. I've now got 4 objects created. The next thing I do is I have to do this new string builder. So that gives me a string builder object and a character array. So I then take my string 1, and I'm doing value of, so that goes in there as part of the constructor. I'm appending string 2 to it, and I do this by copying data. So I've got a string builder that now has string 1, string 2 inside it. And then I have to do the toString. So I allocate my string S3 with a character array, and I put that data into it. So at this point, I've allocated 8 objects in order to do 3 lines of code. Now, once this is finished, it's only the bit at the right-hand side that I want, so the rest of it can go away. I can get rid of string 1, I can get rid of string 2, I can get rid of the string builder, and I've allocated 8 objects and cleaned up 6 objects in order to do a very, very simple bit of code. So you burn through objects very, very quickly when you're writing code if you don't think about trying to make sure you don't burn through objects. Now, there's actually something that the JVM does on your behalf here called string interning. So in order to prevent you having to create and destroy all of those objects, the JVM decides to handle strings slightly differently. So what it does is it stores unique strings, what those basically defined inside quotes, inside an internal data collection, because we know they're going to get used several times. And string keys are often used inside hash maps to do lookup, so we do string comparison. And it's much cheaper to keep a copy of them. So you only ever reference your data structure of strings. You don't create multiple copies of them. So in that case, we don't actually need to allocate S1 and S2 because we've already got a copy of it in memory inside the JVM. Now, even more than that, in the compiler, what it can do is, because you have string 1 and it's defined, and string 2 and it's defined, and you've got a plus operator, it will actually work out at compile time what the total is and store that as a result, because it knows you're using constant values. If you'd done a lookup to get the string, it wouldn't be able to do that. So basically, the JVM is minimizing the amount of allocations you've got to do by caching on your behalf. So the way you minimize allocation and destruction is to cache data. So the summary is, whenever you write code, you actually create and destroy a huge amount of objects, and you do so very, very quickly. That's why generational GC is there, to collect only young, newly created objects frequently. And the side effect of having to do that is a performance tax on your application. Right? The time spent in GC, the GC overhead, is basically a tax on your application. So by reducing the amount of allocations, by reusing objects, you reduce that garbage collection tax. And it is possible that that will actually reduce your overall memory usage because you're not creating the same data several times over. You have one copy of it stored in memory. Okay, so object caching. when you cache data, you're going to put it into a collection. It's the usual way of doing it. And there's a whole range of different collections available to you. Some of the more commonly used ones are on the slide there. So there are many more than those. There's the new collections in Java 7, more of them coming in 8. And we heard this morning at the community keynote that Goldman Sachs are writing their own collection classes and so on. But hash set, hash map, hash table, linked list, array list, these are probably the most commonly used collections when people are writing code. And they've got a range of different function, right? Hash map gives you much more function than array list does. And unsurprisingly, it's got an increase in size. So the more function you have in the collections, normally the bigger it's going to be in terms of memory. So using the right collection usually gives you a way of minimizing your memory usage. So what we'll do is we'll actually have a look at some of those in detail. So hash map. So hash map's an implementation of the map interface. So this gives you key value pairs in memory where you can look up a value against a key and it gives you the stored value for it. Now, the amount of memory that uses, so first of all, when you create a new hash map, and just do new hash map without putting any data inside it, what you do is you get a hash map object, and that references an array of hash map entry objects, and its default size is 16. So you've got a hash map object and a 16-element array, so 2 objects allocated as a result of calling new hash map. Its total size is 128 bytes. So you've got a hash map with 16 entries in it by default when you create it. You can specify its size, but if you don't, it's at 16, and it's going to use 128 bytes even before you store any memory inside it. Each time you put data inside it, you have to create one of these hash map entry objects to store your key value pairs. So to begin with, we've got our hash map object, and we've got our 16-element array of hash map entry objects. So we've got our 2 objects. Now, as I said, when you want to put data into it, you create a hash map entry object. So when you do put, it creates one of these for you. Inside that entry object, you'll have an int, which is its key hash. You'll have an object for next, an object for key, and an object for value. And your key value pair goes into the key and value fields. So that's an extra 32 bytes of overhead just for the hash map entry object, and then you put the key and value into it. So there's a lot of overhead. And in fact, if you have a 10,000 entry hash map, there's an overhead of 360K just for the hash map, the array of hash map entry objects, and the hash map entry objects before you even start looking at your key value pairs, which is your real data. So that's a third of a megabyte's worth of overhead before you're storing your data. So what that looks like is this. And what I've done is the objects which are overhead are in blue. So we've got our hash map and our array of hash map entry objects. And as you do a put, we create a hash map entry object that goes into that array, and that's got a reference to a key and a value, which is your real data. So when we add another one, we get a second entry in the array, so another hash map entry object, a key, and a value inside it. So at this point, we've got 4 objects of overhead and 4 objects worth of data. And again, you put your third one in, and the same thing happens, and it grows. Now, if you've got what's called a hash collision, so your key values are too close to each other in type, what happens is you end up starting to get a linked list. So this is where we have a next pointer from the hash map entry. So if you've got a hash collision, it will point to the next hash map entry object. So we've now got to a point where we've got 6 objects of overhead and 8 objects of value. So the more data you store in a hash map, the more it becomes efficient in terms of memory usage. More data to overhead ratio. Okay, next, linked lists. So a linked list is an implementation of the list interface, and it's a traversable list of memory. So when you create a linked list, doing just new linked list, you get a linked list object, and like we did before, you get a child object, which is your linked list entry. Now, there's no array here, which means we're not having a separate array object. It's just the linked list object, which is size 48. Its default capacity is 1 entry, so you're not having 16 created for you, even though you're not putting anything in it. So it's correctly sized. So linked lists are actually far more memory efficient than hash maps are. So to begin with, we have our linked list object. And that's all you've got when you create a new linked list. Now, in the same way for hash map, when you want to store data, we have a wrapper object that your data goes into. We have a linked list entry object, which has 3 values inside it: previous, next, and your data, the entry. So 1 bit of data, 2 bits of overhead. So every time you put an entry into a linked list, there's 24 bytes of overhead plus your data. And for a 10,000 entry linked list, the overhead is 240K. So it was 360 for a hash map, it's 240 for a linked list. So linked lists are more memory efficient. They're not more efficient in terms of performance. Because with a hash map, you should be able to go to your hash map, do a lookup of its key, and it only takes 1 step down the hierarchy to find that key entry. With a linked list, you may have to traverse the entire list. So linked lists take less memory, but it can take longer to find your entry inside the linked list. So what that looks like is this. You have your linked list object, which is just overhead, so that's blue. And as you add values into it, you get a linked list entry object and your value. So for the first entry, our overhead's 2 to 1. For a hash map, it was 3 to 2. And as you put more entries in it, the overhead gets better because we have more green to blue ratio. Okay, next, array lists. So an array list is really just an array and a wrapper object which knows how to manage and access data from that array. So when you create an array list, doing just new array list, it creates an array of size 10. So for hash map, its default size was 16. For linked list, its default size is 0, and you put objects into it. For array list, the default size is 10. And that means when it's empty, its size is 88 bytes. Now, I have to say, I've got no idea who worked out what the default value should be. For hash map, it's 16. For a hash table, I think it's like 12. For an array list, it's 10. For other things, it's 16. For some, it's 8. There's a huge range of default sizes. And the only way to know what it is, really, is to look it up in a book somewhere where someone stored it or go to the source code. There's no consistency. But again, because when you put something into an array list, there is no overhead of having like a hash map entry object or a linked list entry object. The overhead of a 10,000 entry array list is actually only 40K. So it was 360K for a hash map, 240K for a linked list, and 40K for an array list. So if you can use an array list, it's significantly smaller than the other 2 collection types. And that's because in terms of a structure, it looks like this. You have your array list, and then you just have a huge array of your entries. So there's very little blue to green ratio. So lots of data, not a lot of overhead. Okay, so other types of collections. String buffer, going back to our add one string to another, it uses a string builder. String builders and string buffers are really other types of collections because you've got an array of characters, that's your collection, and it manages that collection for you. So it's very much like an array list. Unfortunately, an array list starts off with 10 entries in it when it's empty. A string buffer has 16. So again, it's another example of you need to know what the default size is. So creating a string buffer with nothing in it has 16 characters that you can use. Its empty size is 72 bytes. And the overhead is just 24 bytes for a string buffer. Its overall overhead is the same as for an array list. It's 40K for a 10,000 entry string buffer. And again, it looks pretty much like an array list. So again, it's an example of you can have a more efficient collection if you want to, and string buffers basically look like collections. Okay, so there's our range of default capacities: hash set 16, hash map 16, hash table 11, array list 10, string buffer 16. So there's a range of them, and there's a range of empty sizes as a result, and there's a range of 10K overhead. So the overhead if you've got 10,000 entries. You'll notice basically the three which are hashing and therefore have fast access to your data are big. Linked lists sit in the middle. Given the overhead and given that they've got linear access rates, you go to your linked list and you have to walk down it until you find your data, they're often not worth using. And then you've got array list and string buffer, which are much, much smaller if you can store your data in those formats. So hash collections versus others. I said the top three were very big. And in terms of overhead, they are 9 times more overhead than an array list. So array lists are much more memory efficient if you can use them. But as I said, the access time for a hash table or a hash map or a hash set should be linear. There's only one set of operations required to actually get to your data. With a linked list, you may have to traverse all of your data. With an array list, you may have to know which slot it's in ahead of time. So there's a range of different collections you can choose. You may want to use hash map or hash set, but you should use them because you know it's the right thing for you to use. We actually do a lot of analysis of people's applications looking for gaps in memory usage. And you'll see this later, but what typically happens is when someone writes code, they always use the same collection type. Right? People get used to writing new hash map or new hash table, particularly hash table or hash map. You're either one or the other. You're either a hash table guy or you're a hash map guy. Right? And that's just what happens. Now, I said that each of these collections has got a default size. And the problem with that is, if I was to create a new string buffer, which I said has a default size of 16, and what I put into it is my string's much less in size than the 16 entries. So I've actually got I think it's like 9 characters of my string. But I've got 16 entries in order to put that 9 characters in it. So I've got 7 additional character entries which I'm not using. So in this case, I'm using an extra 112 bytes worth of memory for nothing. Right? This just sat there as reserved, used, but empty memory. Now, that actually makes sense in terms of a string buffer, because you're supposed to be adding things to your string buffer. That's why you're using it, to build a bigger string. But what happens is, so I've got my string buffer with default size of 16, and I've got my string in it using 9 characters. Now, what happens if I want to start adding more content into my string? So I want to put in my string of text. So I've got my string of, and as I start adding the characters for text, I've got the problem that I've hit 16, it's full, and I want to put an extra character in. So when I add the T for my string of text, what happens is it doubles in size. It goes from being 16 entries to 32 entries for me to put my 1 extra character in. So I've now gone from having 7 spare characters when I had my string to having 15 spare characters with my string of text in. So it's doubled the size of my collection in order to put 1 extra character in. Now, that doesn't sound like too much of a problem in all honesty, right? You think about it and it's like, okay, 15 characters, that's what? I don't know, maybe 200 bytes. It's not really a huge deal. But think about taking big SOAP messages which you're going to send somewhere. And if you've got a big string for a SOAP message that's 16 megabytes in size, and I add 1 extra character in it, I'm going to allocate a 32 megabyte string buffer in order to put it in there. So I'm now wasting 15 meg of empty space because it's doubled in size. And again, in the same way that the default size for collections is 16, 16, 11, 1, 10, 16, it seems to just be, well, I've got a magic 8 ball and it's whatever it said. They've done the same thing for the expansion algorithm. Most of the hash sets double in size, apart from hash table. That doubles and adds 1. Linked lists grow linearly, so that's good. If I put an extra item in, I only pay for my extra item. I'd never have to pay for empty space. Array lists, they grow by 50%. And string buffers, they double. So again, the only way to really know how it's going to grow is to look it up in a book, or if you've got access, go and look at it in the code. So there is a trade-off of memory footprint versus performance, right? We see that with using hash collections versus array lists or the like. Using hash tables, they are 9 times the size of an array list, but you've got much faster access to your data. So it may well be that 98% of the time, a hash collection is actually what you want to use, rather than an array list. If you can use an array list, it's much, much smaller. But really the important thing is you should be making that decision because you know it's the right collection to use, not because you're a hash map guy and that's what you do. The other problem is when you put more data into an array, it's going to double in size or add 50%. So it's important to make sure that you've sized it correctly to begin with, so there's no spare space. And if you have an idea of how big that collection is going to need to be in total, right, if you're only ever going to store 6 items in this collection, create it at size 6. Right, you want to try and size your collection correctly for what your application actually does. Okay, so finally, application analysis. So we've said there's an overhead to all of your data, right? Objects are much bigger than the data you put in it. And we've said that creating temporary objects causes garbage collection a problem. So really, you do want to try and cache data where you can. And where you are caching data, we want to make sure you're using the right collection and that you've sized it correctly so there's no empty space. And that we try and avoid it doubling size or growing by 50% when you put extra items in. So we want to be able to identify things in your application which don't meet those rules, where it's got lots of empty space in it is a good starting point, or where it's the wrong collection type and you can use a lower head collection type inside your application. So the interesting thing is that I said that the overhead of a hash map is like 360K for 10,000 entries. So that's actually, a third of a megabyte. It's not a huge amount of data. So am I just talking through this because I can and it's not that interesting? It's not going to really help you. So we actually went through an application and tried to quantify the amount of wasted memory and the number of collections that are being used. So we ran the IBM Webster Application Server. I work for IBM, so I have to do everything with my technology. It's like the rule. If I came in here and talked about Tomcat, I'd probably get fired. So we did this with Webster Application Server with Plants by WebSphere, which is a sample application that gets shipped with it. And this was done on WebSphere 7, so it's a couple of releases old. We're now on 8.5.5. I ran a load test with 5 users, and that had heap usage of 206 meg. So this wasn't a big, massive application, but it was using 200 megs worth of memory. So what we found was there was 262,000 instances of HashMap being used at that point in time. And the total memory used by the hash table and the hash table entry objects was 26.5 meg. That doesn't include the useful data stored inside it. That's just the overhead of the hash table objects and the hash table entry objects. Next, we found that there was 20,500 instances of weak hash map. And that was totaling an overhead of 12.6 meg. There was 10,500 hash maps. There was 9,500 array lists, 1,500 hash sets, 1,250 vectors, over 1,000 linked lists, 299 tree maps, and a grand total of 306,000 collections on the Java heap with a total overhead of 42.9 meg. So when we looked at this, the first thing we said was, the guy who wrote Plants by WebSphere, he's a hash table guy. But then we were scared because it's sort of like 16% of the live data on the heap. is just the overhead of the collections and not the data inside it, which is the useful thing. So we're wasting 42.9 megabytes to manage our data rather than have the data itself. So we thought there's probably some gains to be had here. So the first thing we did was we broke out Eclipse Memory Analyzer. Does anybody know Eclipse Memory Analyzer? Okay, so what it does is it will take an hprof dump from Hotspot. On IBM, we use operating system core files, so a core file on Linux, a mini dump on Windows, and we load that into Memory Analyzer instead. But it achieves the same thing. So we load that in, and inside Memory Analyzer, it's got a few functions that let you go through all of the memory from your Java application and take a look and see what it's doing. And in particular, it's got an option to look at Java collections. And inside Java collections, one of the interesting ones is called collection fill ratio. And this tells me how full my collection is. Is it empty? Is it 10% full, 20% full, 30% full, and so on? So I can choose to run collection fill ratio against all of the Java collections on the heap. Now, it does give you some filter options. So I know the guy who wrote this code was a hash table guy, so I'm only going to look for hash tables. So I can say only find Java util hash table objects on the heap and give me a report about how full they are. So of my 127,000 hash tables, 127,000 of them were empty. They had a fill ratio of 0. So someone had been creating hash tables, not storing any data in them. So they'd done just hash table, my hash table equals new hash table. And they'd forgotten to do hash table put. Or they hadn't got any data to put into it yet. So that's roughly 50% of the hash tables are completely empty. We then had 95,000 of them, which were less than 20% full. So if their size is 16, that means we've got less than, 3 entries in it. 39,000 of them were less than 40% full. And then we had a couple which actually had a reasonable amount of data in them. And in terms of what Memory Analyzer tells you, shallow heap is the overhead of the hash map entry objects themselves. And the retain heap is that object and everything it points to afterwards, so everything it references. So the retained heap for all of the empty ones, that tells me how much memory I could save if I never allocated those 127,000 empty hash tables. Okay, so from that, I can actually select a row. So I can select the row where they're all empty. They've got a fill ratio of 0. And I can say list objects with outgoing or incoming references. Outgoing references will show you the list of the hash table objects and what's inside the hash tables. So you can see its contents. But we know they're empty, so their contents are nothing useful. If we do it with incoming references, we get to see which objects are pointing to the hash table. So basically, what code owns the hash table. And when I do that, I can see that I've got a hash table. It's being referenced from a memory session. And that seems to be true in a lot of cases. So I now know it's the memory session which has got the empty hash table in it. So it's a hash table that's being created to store session data, but there's no session data. And we went through and we actually did this empty analysis for all of the collections on the heap. And we found from hash table, of the 262,000 of them, 48% of them were completely empty. For weak hash map, 99.5% of them were completely empty. So almost every single weak hash map was empty. For hash map, it was 71%. Array list, it was 48%. Hash set, 55%, and so on. So on average, we're looking at over 50% of those collections were completely empty. So in the JDK team, right, we know that sometimes you don't actually know what data is going to be put into your collection. Right? If you're creating a framework and you've got an API for people to store data, you don't know how much they're going to store. So we want to see whether we can do things at the JDK level that's going to minimize the overhead of memory and try and be more intelligent ourselves. And weak hash map was actually a really good example. Right? We said 99.5% empty. So almost all of them were completely empty. And when you get a weak hash map, it's kind of a unique collection because inside your weak hash map, you get an array of weak hash map entries size 16. So it's exactly the same as a hash map. Right? 16 array when it's empty and an owning weak hash map object. But you've also got a reference queue. And that reference queue is used to get rid of objects when they're not being used anymore. Right? Weak hash maps are designed to be self-evicting. Now, you only actually need that reference queue to do evicting data if there's some data inside it. Right? If there's no data for us to evict, we don't need a reference queue to do that. And the reference queue is actually quite big. The size of a reference queue is 560 bytes, out of a total 688 bytes for the weak hash map. So we did what we thought was the sensible thing. We did lazy allocation of the reference queue. It's not until someone puts something in the weak hash map do we choose to create the reference queue in order to be able to take things out of the hash map. And that saved 10.9 megabytes in our example. And we were using, 210 meg? So we saved 5% just from a single change to say, let's lazily allocate the reference queue the moment someone puts data into my collection. So finally, techniques for minimizing memory. Lazy allocation of collections is probably the first and best thing that you can do. So there's no point creating a collection until you've got some data to put in it. Avoid all of those empty collections by just not creating them. Where you would do your first hash table put, you can create your hash table and then put something in it. Until you're putting data in, there's no need to have the hash table at all. It's very, very common to have it in the initializer or the constructor of an owning object rather than when it's actually required. So secondly, if you're only storing one object, you could actually just store that object and not put it in a collection because there's only one of them. And that saves you the overhead of the wrapping objects. So in the hash map, that saves you the hash map object and the array of hash map entries. So you're down to single objects. Thirdly, size your collections correctly. So if you're only ever going to store 2 entries inside a collection like a hash map, you can create it with a size. And the reason for doing that is you're not going to have, if you're only going to put 2 in there, you're not going to have 14 empty entries in your array which you're never going to use. So you get to save memory there. Item number 4, avoid expansion of collections due to the doubling or the extra 50% algorithm. If there's a chance it's going to grow, you want to try and minimize the doubling and wasting a huge amount of spare space afterwards. That's not always easy to do. And in all honesty, it would be really nice if the collections had a pluggable expansion algorithm in. So you could say, I know that most of my collections are going to be under half a meg. And if they're going to be over half a meg, then grow them in extensive 1 meg at a time, rather than continuing to double. But that's not there. So it's kind of, if you know there's a maximum size it's going to grow to, maybe allocating it at the maximum size is the right thing to do. And finally, at the bottom, I didn't cover this, but I should probably add a couple of slides in for it. We said that if you've got a string buffer, that's size 16, you've got 16 characters in it, and you want to add 1 more, it doubles in size. That's fine. But what happens if you remove entries from a collection? Once it's grown, if I remove entries, does it shrink? The answer is no. So it always stays at the high watermark, the largest size it's ever expanded to. And if you want to make it smaller, the only way to do that is to create a new collection at the smaller size and copy the data over. So you have to resize that collection yourself. It's not done for you. Yes?
The collection and the string buffers, how do they expand? Do they create a new, do they allocate a new array copy or do they?
Yeah, so the question is, when you've got array type structures like an array list or a string buffer, and it wants to double in size or grow by 50%, how does it do that? So yes, what it does is it creates a new array at the new size and copies the old data over. So it's a create and copy. It doesn't dynamically extend as such. Yes?
For hash maps, I see you size it the same as to fill it 100%. Should you really be doing that in practice? Because wouldn't that lead to a lot of collisions for a hash map if you're using it for performance?
So the question is, if you're using a hash map, should you really size it correctly for the number of entries, because that gives a greater chance you're going to have hash collisions and have that linked list for access time. So you're completely correct. As I said, there's a trade-off between memory and performance. So for hash maps, yes, there's an argument you should have extra capacity. Your alternative is to implement your own hash algorithm for it if you know what your data is. So there's ways of minimizing that if you want to. But yes, you're right. If you correctly size it, you've got a much better chance of having a hash collision as you're putting entries in. Yes?
So, typically in a method, when you try to return a collection, it's not guaranteed the method is going to return a meaningful value for the empty collection. A lot of times people do that. So, in that scenario, what's your recommendation on handling?
Sorry, I didn't get the first bit.
So, in a method like return a collection, so a lot of times you may not have meaningful values, that's to return just an empty collection to avoid that one.
So the question is, often some people return an empty collection rather than null, because then you don't have to handle the null pointer exception. So you could just change your design pattern. Yeah, you're right. But you could equally do that lazily. So rather than creating your collection when you initialize the wrapper that's going to return the collection, you wait until someone actually asks for it and allocate it at that point and return it empty. You still have an empty collection. And then the second thing is, if you know there's a good chance it's going to be empty because that happens, then maybe the correct size for it is 1, or created it at a very small size. Anything else? Okay. Yes.
I just a little curious. That is current IBM WebSphere application. The situation you just explained.
So the question is, the slide I showed about the WebSphere application server, is that the current situation? So that was WebSphere 7 that we did the analysis on. The weak hash map change that we did went into WebSphere 8. Since then, there's been 8 and 8.5.5, so we've moved on a lot. And yes, we do a lot of work now to reduce our memory footprint. So usually when IBM releases a product, right, we have performance criteria we have to meet before we can release. One of them is that you have to be faster than you were the previous release. Right? Performance has to get better. We now have 2 others that we have to do. Startup has to be faster. So each release of our application server has to start up faster than the previous one. And our third one is the memory footprint has to be smaller. So each release, even with the new extra features going in, we have to go faster, start faster, and be smaller. Yeah, it's not a fun job. Yeah.
In addition to the Eclipse tool that you showed, is there any other standard tool that works with across all the JDK implementations?
So the question was, I showed Eclipse Memory Analyzer tool. Is there other tools which will do that? That works across implementations, across JVM vendors. So firstly, Memory Analyzer does work for every single vendor. Right? It works for Hotspot. It works for the IBM JDK. It may not work for JRocket, actually. I don't know if JRocket implements the HProf format heap dump, but JRocket's going away anyway. So, but I do know that Oracle, inside Mission Control, is starting to build a tool called JOverhead or something. And that tries to actually implement exactly the same thing, looking for empty collections. But generally, across the board, Memory Analyzer is the one that's being used. And it's not just by IBM. It's an Eclipse project. We just contribute to it. Yes?
Simple question. You have HashMap, MyHashMap, equals new HashMap. Do you say anything by instantiating HashMap, MyHashmap equals null?
So creating it as a null entry.
Say a new HashMap, just say null.
Yeah.
Does that say anything?
I've no idea. So the question is, can you create a new hash map as null? Maybe we should talk afterwards so I've got time to think about the question. Yeah. Okay, so the summary is there's significant overhead to your application and particularly to your data. Every time you do a new operator, there's data being created by the JVM in order to manage your memory. Applications almost always have the wrong collection type in use because people are the hash table guy. They've got collections which are either empty or near empty. And by being careful about the structure that you choose, the collection that you choose, the size that it is, and actually caching where you can cache, can improve your memory efficiency. And if you want to try and do that for your application, Memory Analyzer Tool is the thing I would recommend to do that with. And that's the URL for, there's an IBM web page that explains all of the sessions that we're doing, and there's a link off there which lets you download the slides for all of the IBM presentations. It in effect goes through to my SlideShare account for my presentation, so if you try and find me on SlideShare, you will find the presentation.